Kuzampo, Bhutan e-learning project welcomes children to this lesson. I am Sumitra Subba. This lesson is a physics lesson from Key Stage 5 for classes 11 and 12. In the last few decades, electronics have taken over a major part of our life. We are surrounded by electronics at home, in schools, in offices, and everywhere. Have you ever wondered what these electronics are made up of? Remember, the essential components of these electronics are made up of semiconductor material. You will find semiconductor material virtually in all the electronic devices like television, mobile phones, ATM machines, computers, solar panels, calculators, rice cookers, and many more. So today we are going to learn about different types of semiconductors. So let us have a look at the lesson objectives. By the end of this lesson, you should be able to define semiconductor, state different types of semiconductor, explain the different types of semiconductor, and appreciate the applications of semiconductors in our day-to-day life. Now let's look at the definition of semiconductor. Semiconductor is a substance whose conductivity lies between that of a conductor and an insulator. I hope you know about conductor and insulator. Conductor is a substance which allows easy flow of current through them, whereas insulators, they do not allow any current to flow through them. So conductivity of semiconductor lies between conductor and insulator. The examples of semiconductors are germanium and silicon. These are the common examples. Now before we go to the different types of semiconductor, let us look at energy band. In an isolated free atom, you might have seen they have well-defined energy labels like K label, L label, S label, etc. like you see in the diagram. But in a crystal, they do not have well-defined energy labels because in a crystal, there are many atoms squeezed in a very small space. As a result, their energy levels interact and they split up into numerous close and almost continuous energy levels called energy band, as you can see in the diagram. Now let's look at the definition of energy band. Energy bands are groups of energy levels separated by band gaps called forbidden gaps or forbidden bands. And the energy gap or the energy band where no electrons are allowed to stay or where no electrons are found is called forbidden gap or forbidden band. You will usually find this forbidden energy band between conduction band and valence band. Now let's look at the definition of valence band. The energy band consisting of series of energy levels containing valence electrons is called valence band. So this energy band contains valence electrons. Next we have conduction band. Conduction band is the lowest unfilled energy band lying just above the valence band. So this conduction band is the lowest unfilled band just above the valence band. Now let's look at the energy band diagrams of conductors, insulators and semiconductors. As you can see in the diagram, the lower band is the valence band. The upper band is the conduction band. And the gap in between the lower band and the upper band is called the forbidden gap. Now look at the energy band diagrams of these three types of substances, that is conductor, insulator and semiconductor. Can you find differences between them? Did you find any differences? Yes, they have differences. If you look at the diagram of conductor, the conduction band and the valence band, they are lying side by side. That means there is no forbidden gap between the valence band and the conduction band. If you look at the energy band diagram of insulator, you can see a large forbidden gap between the lower valence band and the upper conduction band. Again, if you look at the energy band diagram of semiconductor, the gap, that is the forbidden gap between the valence band and the conduction band, is quite smaller compared to that of insulator. So from here we can compare their conductivities. So since in the case of conductors there is no gap between the conduction band and the valence band, so electrons from valence band can easily move to the conduction band for conduction of electric current. Remember, for conduction of electric current, there should be some free electrons available in the conduction band. Then if you look at the diagram of insulator, since the gap between the valence band and the conduction band is quite large, so the electrons cannot jump from the valence band to the conduction band. So insulators are bad conductors of electricity. Now if you look at semiconductor, there is a gap between the valence band and the conduction band, but it is quite small, so electrons upon gaining some energy can jump to the conduction band from the valence band and they can conduct current under certain conditions. Now next, let's look at the different types of semiconductor. Semiconductor is broadly classified into two types, that is intrinsic semiconductor and extrinsic semiconductor. Extrinsic semiconductor is again divided into two types, p-type and n-type semiconductor. Now let's look at different types of semiconductors one by one. First, let us look at the definition of intrinsic semiconductor. The pure semiconductor is called an intrinsic semiconductor. It does not have any impurities in them. Intrinsic semiconductors, they behave as conductor at higher temperature and they behave as perfect insulator at 0 Kelvin. Examples are pure semiconductors like germanium and silicon, which do not have any impurities in them. Now let's look at the crystal of intrinsic semiconductor. As you can see in the diagram, silicon has 4 valence electrons since it belongs to 4th group in the periodic table, and it utilizes all the 4 valence electrons in forming 4 covalent bonds with the neighboring 4 silicon atoms, as you can clearly see in the diagram. So now silicon atom does not have any free electron for conduction of current. So this is at the normal temperature. So what happens is, now when you increase the temperature, when the temperature is raised due to thermal agitation, some of these covalent bonds might break and some free electrons and holes are created. These are called minority charge carriers in intrinsic semiconductors. So due to this charge carriers at higher temperature, intrinsic semiconductor behaves as a conductor. They conduct electric current to some extent, but the electric current, each of the order of only microampere, it is very small. So usually such semiconductors are not of much use in practical. Now let's look at the energy band diagram of intrinsic semiconductor. We have already looked at the energy band diagram of semiconductor in the beginning, so it is same as that. So here also we have valence band at the bottom, and then we have the conduction band at the top, and there is a gap, forbidden gap in the middle. And you can see here, as the temperature is raised, what happens is some of the electrons from the valence band, on gaining energy, they jump to the conduction band, and electrons, that is free electrons, are created in the conduction band, and simultaneously some holes are created in the valence band. Holes are the sites which are deficit of electrons, which have lost the electrons, and holes have positive charge just like protons, but they are not protons, but their charge is equivalent to positive charge. And holes also conduct current just like electrons. They can also move within the semiconductor for the conduction of electric current. And this phenomenon of generation of electron and holes simultaneously in the conduction band and the valence band is called electron-hole pair generation. So this is how the intrinsic semiconductor conducts current at higher temperature. That is when the temperature is raised. Now next, let's look at extrinsic semiconductor. When a small amount of impurity, maybe pentavalent impurity or trivalent impurity, is added to pure semiconductor, then the conductivity of the semiconductor increases. Such a semiconductor is called extrinsic semiconductor. Remember, intrinsic is the pure semiconductor. Now, extrinsic is impure semiconductor because it contains some pentavalent or trivalent impurities. The process of adding impurity to this pure semiconductor in a controlled manner is called doping, and the impurity atoms which are added are called dopants. Remember, the process is doping and the impurity atoms which are added are called dopants. And next, let's look at the definition of charge carriers. We have two types of charge carriers in semiconductors. They are majority charge carrier and minority charge carrier. The charge carriers which are added externally are called majority charge carriers. The charge carriers created by breaking of covalent bonds or by raising the temperature are called minority charge carriers. Now let's look at the first type of extrinsic semiconductor, that is n-type semiconductor. If a pentavalent impurity is added to the pure semiconductor like pure silicon or pure germanium, then the semiconductor that we get as a result is called n-type semiconductor. In such type of semiconductor, the conductivity is due to the surplus electrons that they get from the impurity. That is the pentavalent impurity. Pentavalent impurity can be phosphorus. Now let's look at the crystal of n-type semiconductor. So I already showed you the crystal of pure intrinsic semiconductor. Now see the difference between the intrinsic semiconductor and n-type extrinsic semiconductor. What difference do you find? Yes, you might have found the impurity atom in this diagram of n-type semiconductor. Here also silicon has 4 valence electrons. So it utilizes all the 4 valence electrons in forming 4 covalent bonds with the 4 neighboring atoms. Now the pentavalent impurity atom added here is phosphorus. Phosphorus has 5 valence electrons. They belong to 5th group in the periodic table. So out of these 5 valence electrons, phosphorus uses 4 valence electrons in forming 4 bonds with the 4 neighboring silicon atoms. Now it is left with 1 electron. This free electron is responsible for the conduction of electric current in n-type semiconductor. So in this manner, if you add more impurities, so more surplus electrons will be added in n-type semiconductor, and this helps in the conduction of electric current in n-type semiconductors. Now let's look at the energy band diagram of n-type semiconductor. The lower band is the valence band, then the upper band is the conduction band, and you can see there is a forbidden gap in between the valence band and the conduction band. But there is a difference in the energy band diagram of intrinsic semiconductor and this n-type semiconductor. Did you see the difference? Yes, you can see there is one more energy state or energy level just below the conduction band, which is called donor level. Remember, in n-type semiconductor we have pentavalent impurity, which gives electrons, extra electrons to the semiconductor. That's why such impurity like phosphorus, which gives or donates their electrons to the semiconductor, are called donor atoms or donors. So due to this, there is an extra energy level in the energy band called donor level, which corresponds to the fifth electron of phosphorus atom. So as you can see in the diagram, the donor level is just below the conduction band. So the electrons from donor level can easily jump to the conduction band and hence help in the conduction of electric current. And then in this manner, the forbidden gap has also now reduced because of the extra energy level, that is donor level, due to the fifth electron of the phosphorus atom. Now let's look at the definition of p-type semiconductor. When a trivalent impurity is added to a pure silicon or germanium, that is the pure semiconductor, then the conductivity of the semiconductor increases due to the increase in the number of holes. Such type of semiconductor is called p-type semiconductor. Now let's look at the crystal of p-type semiconductor. You can see here silicon has again 4 valence electrons. So it utilizes all the 4 valence electrons in forming 4 covalent bonds with the neighboring atoms. But you look at the trivalent impurity atom, that is indium in this case. Indium, since it has got only 3 valence electrons, it uses all the 3 valence electrons, and now it has shortage of 1 electron to form one more covalent bond with the neighboring silicon atom. You can see the red colored dots denote the electrons of the impurity indium atom. Okay, so what indium does is now it now takes electron from the neighboring silicon atom, and a hole is created in the neighboring silicon atom. A hole where there is shortage of electron is created in the neighboring silicon atom. And in such type of semiconductor, that is p-type semiconductor, the conduction of current now takes place due to this hole. These holes can move just like electrons. It can attract electron from the nearby atom and create hole again in the next atom. So in this way, the holes can move around just like electrons. But remember, holes, they have some limitations. They will be able to conduct current, or they will be able to move only within semiconductor. They cannot go out of the semiconductor. But electrons, they can move within the semiconductor as well as out of the semiconductor. So we have looked at the crystal of both the n-type and p-type semiconductor. Remember, in n-type semiconductor, the conduction was due to the extra electron added through the impurity, and now in p-type semiconductor, the conduction is due to the hole created due to the trivalent impurity. And remember, here I have shown in both the cases, I have shown the electrons of impurities in red color, but in reality the electrons are not this color. Okay, all the electrons, they are same. This is just to make you understand that those are the electrons from the impurity atoms. Let's look at the energy band diagram of p-type semiconductor. Again, same thing here. The lower band is the valence band, the upper band is the conduction band, and there is a gap in the middle called the forbidden gap. And again, you can look at the energy band and see the difference between n-type and this p-type. What difference do you see? Can you see any difference between n-type and p-type energy band diagram? Okay, you must have seen there is again one energy level just above the valence band, which is called the acceptor level. Now, why acceptor level? Remember, in n-type we had donor level, and now we have acceptor level. It is again due to the impurity atom. In this p-type semiconductor, the impurity is trivalent. So it accepts one electron from the neighboring silicon atom. So that's why such impurity atoms are called acceptor atoms. Remember, in the case of n-type, the impurity atoms were called donor atoms because they donate or give electrons. Now here we call it acceptor atoms because they accept electron from the semiconductor. Remember, in the case of n-type semiconductor, the impurities were called donor atoms because they donated or they gave the electrons to the semiconductor. But here the impurity, they take or accept electrons from the semiconductor, so they are called acceptor atoms. So here the impurity acceptor atom creates an energy level just above the valence band, which is called acceptor level. Since the acceptor level energy state is just above the valence band, the electrons from valence band can easily go to the acceptor level. So in this case, the forbidden gap is reduced due to this acceptor level formed due to the acceptor impurity atom. Now here we have added a trivalent impurity, so holes were created due to the impurities. Let us look at the charge carriers. Do you remember, in the case of n-type semiconductor, the majority charge carriers were electrons and the minority charge carriers were holes. Now, what do you think will be the majority and minority charge carriers in the case of p-type semiconductor? Can you guess it? Yes, you might have guessed it, right? Okay, here in p-type semiconductor, I gave you example of trivalent impurity as indium. Now, can you think of some more examples for trivalent impurities? I'll give you a hint. You can look at the elements in the third group in the periodic table. Are you able to find it? Yes. Some more examples are aluminium, boron, many more. We have the elements belonging to third group in the periodic table are trivalent impurities. We have learned about different types of semiconductors, intrinsic and extrinsic, and we learned about p-type and n-type semiconductors. Now let's see where are these p-type and n-type semiconductors used or found. Look at this image. Do you recognize it? So what is it? Yes, it is a motherboard, or it is consisting of so many electronic components, circuit elements, all soldered on this board. So you will find such a board in electronics, like in computers, and other devices. If you look at this board carefully, you'll find small components on them, and many of these components are actually made up of semiconductor material. I'll show you some of them here. Like we have this type of component which is called diode. It is made up of both p-type and n-type semiconductor. Then we have a transistor. This is also made up of n-type and p-type semiconductor. Then we have integrated circuit. In short, it's also called IC, or it's also called chip. And this integrated circuit, it is actually made up of so many transistors, diodes, all and many other components, all fabricated on a very tiny chip. So all these are made up of semiconductor material. So these are some examples. You'll find many more. Now let's look at the applications of semiconductor in our day-to-day life. Here semiconductor means I'm referring to the extrinsic semiconductor. The first application is rectification of AC to DC, which means we can convert alternating current to direct current by using a semiconductor like a diode, made up of semiconductor. So where do you find this? You will find this in your electronics. The next is amplification of signals. We use this semiconductor in amplifiers also. In amplifiers, what do is they strengthen the weak signals, like signals coming from long distances, like in telephone calls, like television signals, radio signals. We use amplifiers in these signals. Then we also have this semiconductor material in some devices like solar cells or even solar panels, where the solar energy is being converted into electrical energy. So semiconductor helps us to convert solar energy into electrical energy. Then we can also convert again electrical energy to light energy, like in LED indicators or in LED bulbs. So these are few applications of semiconductors that I have shown here. There are many more applications. You can try to explore some more applications of semiconductor. Let's recapitulate. We learned about energy bands. We learned about different types of semiconductor. We also learned about the construction of different types of semiconductors like n-type and p-type, what they consist of, and we learned about the applications of extrinsic semiconductors in our day-to-day life. Now finally, let's look at some questions. The first question is, what type of semiconductor do you get when you dope a pure silicon crystal with boron atom? So do you get n-type or p-type? You can first find the position of boron in the periodic table, or you can find its valence electron. Then you can easily get the type of semiconductor. Okay, look at number 2. Now, which type of semiconductor do you think is widely used in electronic devices? You can give some reasons. And the third one, you can draw a concept map for today's lesson. Some characteristics of p-type and n-type semiconductors are given. Can you sort out these characteristics for p-type and n-type? The first one is excess of electrons. Then next we have deficiency of electrons. And the third we have majority charge carrier is hole. And then we have majority charge carrier is electron. Dopant donates electrons. And the last one, dopant accepts electrons. So look at this one by one and see to which category of extrinsic semiconductor each of this characteristic belong. Now let's look at the last question. How would you imagine your life without semiconductors? Thank you for attending this lesson. I'll see you all in the next lesson.